There are a few other things I'd like to mention though, and that's the definitions of the main parameters you'll be playing with on here, and what to aim for to capture no such thing's sound. There are essentially two primary sound sources in all of music synthesis. The oscillator, which forms the foundation of subtractive, frequency modulation, and additive synthesis, and then digital playback, the basis of sampling, physical modelling, wavetable, and granular. But the ways in which they are applied to create the finished sound varies dramatically. We'll start with the oscillator. The traditional analog method of generating sound electronically is with an oscillator, an electrical component that produces an electrical alternating current, or AC. A voltage controlled oscillator, VCO, the type used for music synthesis, accepts a direct current as control information to vary the number of cycles generated per second, or its pitch. The only part you should commit to memory is remembering that an oscillator is a repeating waveform with a fundamental frequency and a peak amplitude. Aside from the pitch and its amplitude, one of the most important features for sound design is the shape of its waveform. As we're not using oscillators in the traditional sense here, I'd like to focus on digital playback as a form of sound generation. In wavetable synthesis, single cycle complex waves are stored and looped under the shape of a volume curve. Serum also gives you the option to edit these waves and even to create your own. I'd like to give credit to Appleton and Alonso at New England Digital, who were looking to achieve more realistic and musical sounds within the limited capabilities of their computers, who first thought to divide a sound event up into 3 small chunks, beginning, middle, and end, and store them in a wavetable. Working with single cycle waveforms harkens back to the options of the early days of synthesis, but with a wavetable, the waves are far more complex. Rather than choosing from sine, triangle, square, and saw in a traditional synthesizer sound palette, the options are now expanded to a variety of raw sounds, and now we even have the options to create our own. When a skilled musician plays a sustained note on an instrument like a violin, you will notice that the sound is not static. Rather, it is shaped over time. Once musicians attain a certain level of technical facility on an instrument, there are ways of making a performance musical. Examples of this include a regular shifting over time of the pitch center, vibrato, volume, tremolo, and timbre. I'd like to look at the LFO tool now, used for creating these time-based effects on the synthesizer. We've already covered the oscillator as a device that produces a user-definable waveform in the audible spectrum. A low-frequency oscillator, or LFO, does the same thing but in a range that is typically below 20 Hz and thus not audible on its own. The frequency being produced by the LFO isn't being heard, per se. Rather, its shape is used to manipulate the audible sound in some of the ways that you just saw. It's common, especially on software synths, for there to be more than one LFO available. Although they could be targeting the same variable, a great use of these extras is to set them to a different parameter. The next section we'll come to on a synth is most commonly the envelopes. How a sound's brightness and vibrato, just to name a couple, evolve over time can be manipulated manually with a controller like the modulation wheel, but they can also be defined as a characteristic of a particular patch. This is where the envelope generator, or EG, comes into action. A typical EG provides the following controls. Attack, which is the amount of time it takes for the sound to go from nothing to its maximum level. Decay, the amount of time it takes for a sound to go from the maximum level attained at the end of the attack stages to the volume level set in sustain. Sustain, the volume level, not time duration, at which the sound remains while the key is held following the attack and decay stages. And the release, the amount of time it takes for the sound to go from the sustain level to nothing upon release of the key. More complex envelopes may also include hold stages in one or more of the in-between points. A simple envelope will be labelled ADSR. One that is more complex could be ADHSHR. The hold forces the level to remain at a maximum for a specified duration of time before shifting through the decay stage to the sustain level. Now, there are obviously many other parts to a synthesizer, but I often recommend mastering the fundamentals before proceeding further up the hierarchy. I think working this way makes it easier to remember, making yourself much more comfortable when working with synths. Once you're happy with everything we just went through, filters would be the next element to investigate, followed by modulation, voicing, etc.